Here we're going to be talking about chemical bonding, ionic bonding. So we'll start with Lewis dot symbols, talk about how that pertains to ionic bonding, and then the lattice energy of ionic bonding, and lastly the Born-Haber cycle. So these Lewis dot symbols, they're developed as a way to describe electron configurations. It started with Gilbert Lewis. That atoms combine to achieve a more stable electron configuration. This was the original development of describing some sort of chemical bonding. And the maximum stability can result when an atom is isoelectronic with a noble gas, which is something we're already familiar with. These atoms interact to form compounds. The valence electrons are the only things that interact, and these Lewis dot symbols will depict what that looks like. So these Lewis dot symbols consist of an element's chemical symbol surrounded by dots. Each dot represents a valence electron. Here are the Lewis dot symbols for each individual atom in their ground state. So you can take a look, for example, at hydrogen. Hydrogen has one valence electron, so we put one dot next to it to indicate that. You could look at something else like carbon. Carbon has 4 valence electrons, so you can see that there's 4 dots associated with carbon. Sometimes they are, if they are next to each other, they're considered paired electrons. If they're not next to each other, they're not considered paired electrons. Don't worry too much about that right now. And so these are the ground state electron Lewis dot symbols for each of these elements, and we'll find that we can combine them together in certain ways to represent chemical bonding. So let's try writing Lewis dot symbols for each of the following. So now remember, what we had just seen was all of the electrons in their ground state. Now we're forming ions. These ions, we are going to add or take away electrons in order to form these ions. And again, they're commonly going to form noble gas configurations, right? If they're the ions that we know are most common. So for example, let's take a look at the fluoride ion. We have fluoride in its ground state. It has 7 valence electrons. Okay, so this would be fluoride in its ground state. We need to add 1 electron for the negatively charged ion. So we're going to add 1 extra electron to make F minus. This we are commonly going to put like so. We also need to indicate that that's F minus, right? That's fluoride with a negative charge. So this would be the Lewis dot symbol for fluoride. Potassium ion is a little bit different. So generally with something like fluoride, we would want to also put these in brackets to indicate that that this negative charge is referring to what it is, that chemical symbol. Potassium, on the other hand, potassium has typically has 1 valence electron. So we will simply get rid of that valence electron, so I'm not even going to draw that, but we do need to then indicate the charge. This is K plus. So we do not actually need to put the 8 valence electrons around potassium because it has lost its outermost valence electron. So even though potassium does have a Lewis dot structure, a Lewis dot configuration, that of a noble gas, we do not put those 8 valence electrons there for cations because they've lost their outermost electrons. So then sulfide, similar sort of thing. We could start with its ground state. Its ground state is going to have, let's say, 6 valence electrons. We're going to be adding 2 more, so I'll add those 2 here. Again, we get 8 valence electrons. We're going to want to indicate that that has a 2 minus charge in order to justify having 8 valence electrons. So this would be what that Lewis dot symbol should look like for the sulfide ion. Okay, so we can use this, like I had mentioned before, to talk about ionic bonding. Ionic bonding, if you recall, refers to the electrostatic attraction that holds oppositely charged ions together in an ionic compound. So let's take a look at potassium and iodine. Those can come into contact with each other. Valence electrons can transfer. So potassium will lose its one valent electron. It will be transferred to iodine to form iodide, which is negatively charged. And we can actually show this in the Lewis dot configuration. So if you take a look in the bottom right, we have potassium losing its one valence electron to form K plus and I minus, both of which will have a filled octet. And because of all of this, it's highly exothermic. This compensates for the energy input required to transfer electrons from metal atoms to non-metal atoms. Okay. So this is how we could show that sort of electron transfer. This brings us to lattice energy. This is the amount of energy required to convert a mole of an ionic solid into its constituent ions in the gas phase. This is just a definition, lattice energy. So it's trying to get at how strongly held together are these two ions in an ionic solid. So we can take a look at one of these. So potassium iodide, 632 kilojoules per mole is the lattice energy. So we could set up what that chemical equation would actually look like. And it's potassium iodide, 1 mole of it as a solid, forming K plus as a gas and iodide as a gas. And you can see we have a delta H of 632 kilojoules per mole. It takes quite a bit of energy to rip those two things apart. And this is defined as lattice energy. As you can imagine, that is actually a very bizarre reaction. We typically would not see potassium iodide as a solid forming ions that are gaseous. So directly determining the lattice energy with a chemical experiment, for example, is really challenging to do. So we'll find out how we could actually do that using a different methodology. Okay. So the magnitude of lattice energy is a measure of the ionic compound stability. So the greater that lattice energy, the more stable that compound, the harder it is to pull those ions apart. Here you can see we have a couple examples of lattice energies and how it pertains to some very real physical properties like the melting point, for example. So if you have a much higher lattice energy, it is going to be harder to pull those ions apart. So it will have a higher melting point, for example. So lithium fluoride has a very high lattice energy, and you can see its melting point is quite high. So this, in general, follows this sort of trend, and there are going to be some minor differences. It's not just based on the lattice energy, but it is a really good predictor of some of these physical properties. If we recall, when we talked about ionic bonding in the past, and we had talked about the charge of the two ions mattering and the distance between them to matter. This was the force based on electrostatic attraction or repulsion. So if you take a look at lithium fluoride, here we have the lithium ionic radius and fluoride's radius. And one's a +1 cation, the other one's a -1 anion. So you can see we can plug those values into that force equation. So you have +1 times -1, and then you divide it by essentially the distance between the two squared. So that was again, the force based on the energy, the electrostatic repulsion or attraction energy. So the distance between the two ions matter. So if in all these situations you have a +1 and a -1, the distance between those two matters. So you're going to have a higher lattice energy if the distance between the two atoms are smaller. That would mean if they have smaller ionic radii. A much more major trend would be if instead of having a +1 and a -1 cation and anion respectively, you'd have a +2 and a -2. That's going to be about 4-fold increase in the amount of lattice energy that you would expect. And you can see that on the prior slide, in which something like magnesium oxide was much, much higher than lithium fluoride, for example. And that would be based on the more major trend, which is the increasing charges on those ions. And then the minor trend being the distance between the two. Those distances are going to be predicted based on the ionic radius of these individual ions. Okay, so here we have that example where you have +1, -1, so lithium fluoride, and it has 1,000 kilojoules per mole. And here magnesium oxide, which is a +2, -2, with ions of similar size, have about a 4-fold increase in the lattice energy. So this is going to be a much more major trend. So when we're trying to determine when we're trying to determine lattice energies, which ones will have higher lattice energies, first and foremost, we're going to look at the magnitude of the charges. Then secondly, we're going to look at the ionic radii as these trends. So let's try one of those. Magnesium oxide, calcium oxide, and strontium oxide. Let's try and arrange those in order of increasing lattice energy. So first and foremost, both have a +2 or all of them have a +2 and -2 magnitude for the charges, and that is the more major trend. So that means we need to go to the more minor trends. We need to look at the size differences. Looking at the periodic table, magnesium is going to be smaller than calcium. Calcium will be smaller than strontium. So strontium is the largest, magnesium is the smallest. So magnesium will, since it's the smallest, it's closer together, there's more electrostatic pull. So magnesium oxide will have the highest lattice energy. Oh, and there's an error there, right? Strontium oxide, it needs to be the smallest. Calcium oxide's in the middle. And magnesium oxide should have the strongest lattice energy. So like I had kind of alluded to before, there's a lot going on here, but lattice energy is really hard to determine. If you take a look, you're going for lattice energy, you're going from sodium chloride as a solid to sodium chloride as a solid to sodium as a gas, an ionic gas, and chloride as an ionic gas. That is what we defined as lattice energy. That is not a reaction that we can actually run. So if you recall from in the past, we had Hess's law, and Hess's law really meant it doesn't really matter how you get from the start to the finish. You could determine the delta H if you had a bunch of other reactions that could add up to a new reaction. So there are a bunch of other reactions that we could do that make our way all the way to the lattice energy, okay? Where we can go from sodium chloride all the way to sodium plus, that's gas, and chloride, that's gas. But it requires all of these different steps. And that's how we can actually get the lattice energy, is we can use those other delta H's and add those together to get to what lattice energy is. So this is a way to calculate lattice energy. So you can see we can take sodium chloride. We could split up the here we're breaking the bond for chlorine. Okay, so that's the opposite of this. So you're so this would be a reaction that you could look up in that table. This is the standard enthalpy of formation of sodium chloride, going from sodium as a solid, which is its standard state, and then half Cl2 gas, which again Cl2 is in its standard state. So that would be a reaction that you could look up. Then we're just taking sodium from a solid to sodium as a gas. So this is sublimation of sodium. That's the only difference that we're showing here. So that would be a way to go about that. Okay. Then we're going from 1/2 Cl2 to just Cl. So that's the breaking of that chlorine bond. Okay. And then we're going from sodium gas to Na plus gas. This was called ionization energy. So this is the first ionization energy of sodium. And then lastly, we're going from chlorine gas, that just Cl gas, to Cl minus gas. And that was the electron affinity of chlorine. So you can see these are all reactions that we could potentially find or potentially would know. And we can use those to then calculate the lattice energy of sodium chloride. So even though lattice energy we can't measure directly very easily, because that is not a reaction that we can run, we can use Hess's law in this cycle, which is called the Born-Haber cycle, to ultimately calculate the lattice energy.